Right, J plus 1 here, welcome back. Today we're going to be talking about kinematic equations. Now you'll see these for sure in pretty much every high school physics course and for sure in the first 2 weeks of your freshman physics course in college. Today I'll be talking more about derivation of kinematic equations. Where do they come from? Just what's the source of them. And I'll be using calculus to do this. You can use simpler mathematics to derive the kinematic equations, but it just takes longer. So I'll be doing it the easy way. So talking about kinematic equations, we have 4 variables to consider: position, velocity, time, and acceleration. In more complicated cases, you'll have other variables to consider, like friction and air resistance. And in those cases, your acceleration might not be constant, so the kinematic equations don't quite work. But for your very simple cases, these 4 variables are fine. And acceleration will be constant, so it makes life even easier. So here we go. So let's first talk about velocity and time together. So we know by definition that acceleration is change in velocity with respect to time. So what can we do with this? We can use separation of variables to rewrite this equation as a dt equals dv. You could say you multiplied by dt on both sides. Separation of variables is kind of odd. Notation-wise, this is incorrect. Mathematicians will get very mad at you for this, but technically it works. It's acceptable. I'll do another video explaining separation of variables and why it works. But back to the matter at hand. So now that we have a separation, we have infinitesimals on both sides, we can integrate. So we'll rewrite this as the integral of a dt equals the integral with respect to dv, or v, excuse me. So again, if we're talking about simple case, acceleration is constant, so that just comes right out of the integral. So we have a times the integral with respect to t equals the integral with respect to v. Now what? So both of these equations just have a constant 1 inside them, so they're very simple. And we need limits, of course. So we have, for t, we can say t naught to t final. And for v, we can say v naught to v final. We can also do 0 to delta t and 0 to delta v. I'll do that in the next derivation here to make things easier, but just being pedantic here. So what do we get from both of these integrals? Well, pretty simple. For on the left-hand side, we just have a times tf minus t naught. This integral would just give us a t, and of course we plug in our limits. And same thing on the right side, v final minus v naught. So we can rewrite these as a change in t and a change in v. So we can say a delta t equals delta v. And what you'll often see in your textbooks is that we use a delta t because the change in time is just a change in time. But we want to know final initial velocities. Those are key pieces to know. So we often write this, bringing the v naught to the other side, as v final equals v naught, or just v, v naught plus a delta t. And that's our first kinematic equation. So with this equation, we started with the differential equation a equals dv dt, our definition of acceleration. And so we considered the variables velocity and time. So for our second kinematic equation, we'll use the differential equation. Velocity is defined as a change in position with time. And so I say define as. I should probably technically put 3 lines here because these are our definitions. So the first equation, we considered changing velocity with changing time. Second equation, changing position with changing time. So same procedure here. We do a separation of variables. So we have v dt equals dx. And now what do? Of course we integrate. So the integral of v with respect to t equals integral of dx. So in this case we have something a little different. Our integral with respect to t, v is not a constant. The velocity can change with time. So we can't really do this integral with just a v in there. We have to substitute something for v. And fortunately, we did this with our last problem. So we can substitute our velocity with the initial velocity, which is just a constant, plus the acceleration times change in time. And of course the acceleration is constant and the time is not, but that's our integral. So we'll plug it in. We have v naught plus a t dt. I'll separate these out. There we go. And of course that's equal to the integral with respect to x. And so we need limits again, and again, t naught, we can do t naught to t final or v naught to v final. I'm going to use, well, actually I will use those. But it would be simpler to do 0 to delta t, but that's okay. So again, the right hand side is as we might expect, x final minus x naught. And we could technically separate the left hand side into 2 separate integrals. Again, a constant, and the integral is just going to be v naught times t final minus t initial. So v naught t final minus t naught. And then we have a constant a times t. And if we took the integral of t with respect to t, we would get 1/2 t squared. So plus 1/2 a t final squared minus t naught squared. Oops, that's on the inside of the parentheses. So it looks a little ugly, but we can clean it up. Again, on the right hand side, x final minus x naught will become delta x. On the left hand side, let's say, as I remember, I was saying that we could put the limits as either t naught to t final or 0 to delta t. Well, let's set our t naught as 0. Then this term goes away, and so does this term. So we get v naught delta t plus 1/2 a delta t squared. And that is our second kinematic equation. Alright, on to the third one. So the first equation we considered velocity changing with respect to time. The second equation we considered position changing with respect to time. And you can probably see where I'm going here with this. The final option is the change in velocity with respect to position, or the other way around, but we'll go this way. So that would be dv dx. But what does that equal? I'm not really sure, but I can do a clever trick here to figure this out. So dv dx is a rate of change, so it's the velocity changing with respect to time. What's the other variable we have? We have time. Well, we could write dt dt, the change in time with respect to time, But as you can see, you can consider this a fraction, or you could consider this a number, and it's just going to be 1. So we could multiply these two together, and that would still give us whatever our unknown value is. What is change in velocity with respect to position? So let's write dv dx times dt dt equals question mark. So what can I do here? Well, I could switch one of these infinitesimals, or both, because again, it's strange, it's not technically correct notation, but bear with me. So we can say that dv dx times dt dt is the equivalent of dv dt dt dx. So I switched these two denominators around. And what does that do for us? Well, I know that dv dt is actually acceleration a, and I know that I don't know what dt dx is, but I do know what dx dt is. Dx dt is velocity, so this is actually the inverse of velocity. And of course this is just a constant, so we say our change in velocity with respect to x is equal to the acceleration over the velocity. So now what? Well, this is good, because now I have a rate of change, a constant, and a variable. So I have a differential equation, and I can do what we did in equations with the initial equations 1 and 2. So I can separate variables, put the v's on one side, put the x's on the other side, so I have v times dv equals a dx. So multiplying both sides by v and both sides by dx. So now I integrate as before. We'll say from v naught to v final and from x naught to x final. And so again, the integral of v is going to be 1/2 v squared. So I have 1/2 v final squared minus 1/2 v naught squared. And then here I have a constant acceleration, so I can pull this out of the integral, and then we just get acceleration times x final minus x naught. Now I can simplify this a bit. I'll multiply both sides by 2 to get rid of the 1/2, and I will make x final and minus x naught just a delta x. So let's go over here. So our final answer is going to be v naught final squared minus v initial squared equals 2 times a delta x. And there are your 3 kinematic equations. So I got this information from the physics textbook compiled by Glenn Ellert. And if you're interested in deriving the kinematic equations without calculus, and if you're interested in more introductory physics topics, I highly recommend you visit the Physics Hypertextbook. I'll put the link below. Thanks for watching, and see you next time.